Hello, everyone. Wait, there's more people. All right. Jeff, do you have the handout link, please? All right, so Jeff has posted the handout for today in chat. He'll probably post it again if other people are arriving late. So today we'll be talking about power of a point as well as like radical axis and related topics. If all of this is familiar to you for some reason, you can go try the problems at the end. And then there's some like higher theory at the very end. If you want to try that. But first we're going to talk about some preliminaries. So this is going to be mostly stuff about angles. So there are a few things you should already know. So I wrote something as fact 1.1, which is the inscribed angle theorem. So basically, if you have some circle, and then you have a triangle in it. This circle is called omega. You have a triangle ABC, and you have the center O here. The claim is that this angle right here, angle BAC, is equal to 1/2 of angle BOC. Now this actually isn't too hard to prove. What you can do is you can draw this dashed line, and then you can use the fact that this is the center of the circle, so these things are all equal. You can use the isosceles triangles, and you can derive this angle relation. So this is something quite important. And what can you do with this? Well, you can add another point in. You have a circle. You can add another point here. And I labeled them as A, B, C, D on my handout. And then if you have you know that this angle is half of, if you draw the center in half of this angle. So basically, this angle is half of this arc. You can think of it that way. It's inscribed in this arc. And you also know this angle is also inscribed in this arc. So you know these two angles are equal. And this is actually fact 1.2. So it states that the three conditions are equivalent. A, B, C, D is cyclic. That means that it lies in a circle like this. And then what I've just described is the third fact, which states that angle ADB equals angle ACB. And this is true everywhere else. You also know that like this angle equals this angle. And then the other key property of a cyclic quadrilateral is that angle, say, DAB plus angle DCB is equal to 180 degrees. And the reason for this is I have the center here. I know this angle is inscribed in this arc, and this angle is inscribed in this arc. So when you sum them, you get 360 degrees. Divide by 2, you you get 180. So this is the key properties of a cyclic quadrilateral. So this is a cyclic quadrilateral. And they're very important in math. When you, at like all levels of geometry, I guess, especially at the higher level, often the key players in geometry are these cyclic quadrilaterals. A lot of problems are you have to figure out that four like seemingly unrelated points turn out to actually form a cyclic quadrilateral, and then that will give you some, like you can use maybe this condition is true, which tells you it's cyclic, and then that gives you this condition. And then you can sort of angle chase around and you can get a lot of nice things. So let's see an example of this. This example is actually not easy, but it's called the Japanese Theorem. It illustrates what we need to talk about. So we have this cyclic quadrilateral. And here we define these incenters. So remember, the incenter of a triangle is the intersection of the three angle bisectors. And it's usually denoted I. So this angle equals this angle, this angle equals this angle, this angle equals this angle. And then it's also the center of the inscribed circle right here. And a key property of the incenter, you can go through the angle chasing, but angle BIC is equal to 180 degrees minus angle IBC minus angle ICB. These are angle bisectors, so this is 1/2 of angle B minus 1/2 of angle C. Angle B plus angle C is like 180 degrees minus angle A. So this turns out to be 90 degrees plus 1/2 angle A. So that's the relation between this angle and the top angle there. And what the Japanese theorem says, I'm trying to draw this better, so that if you have this quadrilateral, there are like 4 triangles inside here. And then if you take their incenter, so if you take the incenter of this one, I'll start drawing in like this color. The incenter of this triangle, the incenter of ABC, which is somewhere here, the incenter of ABD, which is somewhere here, incenter of DAC, which is somewhere here. And if you connect them, the claim is that you get a rectangle. And this is rather non-trivial. But the key claim is that these 4 points are actually cyclic. So we're going to call this point I4, I1, I2, I3. And how do you prove this? Well, we want to use fact 1.2, which is the properties of the cyclic quadrilateral. So we have, these are angle bisectors. So we're going to draw in this line and this line. And then, so the claim is that BI4, I1C is cyclic. And the proof, so we're claiming that these 4 points lie on a circle. And the way we prove it is we use fact 1.2. So we want to show this angle equals this angle. So we want to show angle BI4C is equal to angle BI1C. And why is this true? Well, if we look at this picture, we know that this angle is related closely to this like top angle, and we can do the same thing here. I4 is the incenter of ABC. So we know that this angle is actually equal to 90 degrees plus 1/2 angle BAC. And we know that this angle is equal to 90 degrees plus 1/2 angle BDC. But we know another key property of the cyclic quadrilateral ABCD is that these two angles are actually equal. So this angle is equal to this angle. So therefore, this thing is true. All right, so now we have proven that BI4, I1C is cyclic. And then similarly, we also know by the same proof that these 4 points are cyclic, that these 4 points are cyclic, and that these 4 points are cyclic. And now how can we use this? Well, we used one property of the cyclic quadrilateral, which is that these two angles are equal to prove it. Let's use the other property, the 180 degrees. So I guess I'll pick a different color. So if we look at this angle right here and this angle right here, we want to show that this angle is 90 degrees. How do we do this? We can show these two large angles sum to 270 degrees. So this large angle is equal to angle BI4 I1. And by the cyclic quadrilateral, we proved this is equal to 180 degrees minus BCI1. And we know this is an angle bisector right here. So this is equal to 1/2 angle BCD. If you have any questions, feel free to send them to Jeff. And then we can do the same thing over here. Angle BI4 I3 is equal to 180 degrees minus 1/2 angle BAD. That's the same thing on the other side. And now if we combine these, we'll get that the angle we were looking for, angle I1, I4, I3, I1, I4, I3 is equal to 360 degrees minus these two angles combined, angle BI4, I1 minus angle BI4, I3, which is actually equal to the 180s cancel here. So this is actually equal to 1/2 angle BCD plus angle BAD. And we know that this is equal to 180 degrees by the cyclic quadrilateral. So we know this is equal to 90 degrees. So this tells us this angle right here between the blue lines is indeed a right angle. Similarly, we know that these are also right angle. You just repeat the same thing on the other sides. So you know this is a rectangle, and we're done. That was the Japanese theorem. And one thing to note is that anything you discover out of a cyclic quadrilateral, that's actually non-trivial. So like you can try to do like the sum of the three angles of a triangle add to 180. You can try to do like opposite angles or whatever, but none of those will give you the same facts that will come out of discovering a cyclic quadrilateral. So doing that is actually very important if you can find it. All right. So the next thing we're going to talk about is power of a point. So we saw a lot of equal angles earlier, and unsurprisingly, that gives rise to some similar triangles. So if you have a cyclic quadrilateral, A, B, C, D, drawing the diagonals, and we'll call this point P. Then recall by fact 1.2, this angle equals this angle. They both inscribe this arc, BC, and this angle equals this angle. They both inscribe this arc, AD. And then we also know that this angle equals this angle. Since they're opposite angles, it's like symmetric. So this tells you that triangle PAB is similar to triangle PDC. And we can use the length condition that comes out of this, PA over PB equals PD over PC. And this will tell you PA times PC equals PB times PD. This is referred to as like power of a point theorem. So like a theorem that's called power of a point. And how do you generalize this? Well, this actually means if I draw any line here, intersects at X and Y, I can repeat the same thing, and I know this is equal to PX times PY. I can look at like this triangle is similar to this triangle. So it turns out if I pick any point, fixed point P, then I can draw any line I want. I can draw this line right here, and it intersects the circle at 2 points, a fixed circle. Then I know that the product, this times this, is always going to be the same, no matter what. And it turns out that this thing is true no matter where P is. So like P can also be outside the circle. P can be here. And then the same thing will happen. A, B, C, D. I will know that by the 180-degree thing, this thing equals 180 minus this thing, which is equal to this thing. So these two angles are equal. And I also know this angle equals this angle. So that tells me triangle PAB is similar to triangle PCD. And that will give me the same power of a point relation. PA times PD equals PB times PC. And it also works if the thing is tangent. So if I pick a tangent point here, that's because I'll prove it's equal to PA times PD. This angle is inscribed in this arc, which gives me this angle. So we get the similar triangle. So we also know this is PT squared. And this is a tangency point. So let's try to use this once, this power of a point relation. Example 2.2, it's a MOA problem. I think I wrote it. So we have a triangle ABC, and we're going to drop these altitudes, BE and CF. And then we're given that AE is 24, CE is 60, and BF is 31. So how do we apply power of a point? Well, this problem is actually kind of tricky if you don't see the key idea. You can do some like bash stuff with the lengths, but that's not very pretty. So the key idea is that because of these two right angles, we know these two angles are equal. That tells us that these 4 points are actually cyclic. So that means we can draw a circle here. And this actually gives us the power of a point relation. Now we know that AE times AC is equal to AB times AF. We know AE, that's 24. AC is 84. And we know that's equal to AB times AF. Let's call AF x, and we'll call AB x plus 31. If you solve this quadratic equation, you'll get that x equals, it'll equal like 32. So that's one simple application. And here the circle is kind of hidden. So you kind of have to figure that out. So now we'll move on to a definition. So notice how like if you have a circle and you have, if you have a circle, you have a fixed point P, then we know no matter what line we draw, pick arbitrarily, call this line L, we know that Px times Py is constant, not dependent on L, right? So we can actually call this value a name. So we're going to call this constant, we're going to define it. So this means we're going to define it as rho P omega. The circle is omega, the point is P, and this is just some function. I'll call it rho. And this is this quantity right here. This quantity right here we'll call the power of the point P with respect to the circle omega. So give me any point P, give me any circle omega, and then this constant value will be the power. It's actually going to be the absolute value of the power, and you'll see why later. And the reason is, we know that this power is equal to, we know that this power is equal to PT squared, where T is a tangent. So we know this is equal to PT squared. And then by the Pythagorean theorem, we can write this as OP squared minus R squared, where R is the radius of the circle. And this is the way you generally want to define power. So as a recap, we call the power of a circle power of a point with respect to a circle. We define it, so this is defined as OP squared minus R squared. And notice that this is only dependent on the distance from P to the center of the circle and the radius of the circle. And if P is inside the circle, then this value is negative. In any case, Px times Py is always equal to the absolute value of the power. So it would be equal to R squared minus OP squared in this case. And you can also prove that. You can like take this line, AB, and you know that like PA squared, which is PA times PB, is equal to like R squared minus OP squared. Okay, so we're basically defining this power to equal the constant value we found in the power of a point theorem. And we're calling that the power. And a special case, if P is on the circle, then the power of P with respect to the circle is equal to 0, because R squared minus R squared is 0. And let's see if we can use this. This is a theorem, I guess, by Euler. Euler has many, many theorems. This is probably one of his simpler ones. So if you have a triangle, feel free to send your questions to Jeff, by the way, if you have any. Circumcircle O in center I, and the claim is that OI squared is equal to R times R minus 2R. And then consequently, this also tells you R is at least 2R. So R is the big radius. Little r is the little radius here. And how do you prove this? Well, what we're going to start by doing is rearranging this equation. So this is equivalent to OI squared minus R squared is equal to 2RR, negative 2RR. So this is actually equivalent. We recognize this as the power of the point I. So the power of the point I with respect to the circumcircle, I guess we'll call it big omega, is equal to negative 2RR. How do we prove this? Well, we want to express the power of the point I in terms of the like px times py relation. So we're going to draw this line, and we're going to intersect it at the point, what did I call it? I called it D, A, B, C. And we know that this power is equal to negative IA times ID, because I is inside the circle, so it's negative. So now I just want this thing to equal this thing. I'm just going to mix up the colors. How do we do this? Well, first we'll look at what AI is. You can look at this right triangle right here. This little thing is R. So it's equal to R. We know that, sine of angle A over 2, which is this thing, is equal to little r, opposite, over hypotenuse, AI. So this tells you that AI is equal to r over sine of angle A over 2. What else do we know? Well, we can try to calculate ID. Well, first, we claim that this triangle is isosceles, that ID is equal to BD. Why is this true? This is true by angle chasing. We claim that these two angles are equal, which means it's isosceles, so angle BID, well, that's equal to 180 degrees minus angle AIB. This is equal to angle IBA plus angle IAB. This is equal to angle IBA moves to angle IBC because this is an angle bisector. Angle IAB moves to this angle, and then by fact 1.2, it moves down to this angle. So it equals angle CBD. And then this is equal to angle IBD. So this thing is true because BID is an isosceles triangle. So what does this tell you? Well, you know that ID is equal to BD. And BD, if you look at the extended law of sines, you know that BD over sine of angle A over 2 is equal to 2 times the circumradius R. So the extended law of sines states that if you have a triangle, you have an angle here, A, you have a side length, little a, circumradius R, then you know that 2R is equal to, what's it, A over sine angle A. So we're doing the same thing here, but it's slightly different. We notice, we take a look at this triangle right here. We know that this angle is angle A over 2 by the angle bisector. We know that BD over sine of that angle, well, that's going to be 2 times the circumradius R. All right, so now we know that ID, which is equal to BD, is 2R times sine angle A over 2. Remember that we had that AI is equal to little r times little r over sine of angle A over 2, which tells us AI times ID equals 2 big R little r, which is exactly what we want as desired. So this is indeed equal to this power right here, which is what we were trying to prove. If we backtrack the argument, that tells us the power of I is indeed equal to negative 2RR. And that tells us the power of I is equal to OI squared minus R squared, so that's equal to this thing. Rearrange it, we get Euler's theorem as desired. So this is in fact proven. And this gives you the distance between the orthocenter and the incenter in any triangle, which is pretty cool. So that's all of power of a point. So we covered both the power of a point theorem as well as the literal power of a point, which is the function rho. Now we're going to talk about radical axis. So power of a point involves one circle, a radical axis involves 2 circles. And the way we define it is that the given 2 circles, omega 1 and omega 2, we call the radical axis is locus of points, so the set of all points, such that the power, all points P, such that the power of the point P with respect to omega 1 is equal to the power of the point P with respect to omega 2. So to give you an example, we could draw 2 circles here, one circle here, oh, something again, another circle here. And what points would lie on this locus? Well, we know this point lies on the locus because this has power 0 with respect to both. We know this point lies on the locus. And maybe you could draw the common external tangent. And then if you take the midpoint, you know this lies on the locus because the power is this squared is equal to this squared. Same thing here, this external tangent. And then what you'll find out is if these actually lie on a line, the set of all points P lie such that the power with respect to these 2 given circles, omega 1 and omega 2, with centers O1, O2, radii R1, R2. If you're given these two circles, the set of points with the powers equal, this condition, is actually equal to this line. So this line is called the radical axis. And how do you prove this? Well, you actually use Cartesian coordinates, which is somewhat surprising because those don't really show up in geometry unless you're trying to like bash something. But what you know is that if my point P, which I'm trying to say on the locus, is equal to xy, so I'm looking at all points xy, we know that the power with respect to this circle is equal to like x minus a1 squared plus x minus b1 squared. This is equal to, oh, squares inside. This is equal to the distance. This is equal to O1 p squared. And then you subtract r squared, r1 squared. And then the claim is that this is equal to x minus a2 squared plus, oh, this is a y, sorry. So a1, b1 is the coordinates of the center O1. This is equal to y minus b2 squared minus r2 squared. This is equal to O2p squared. So notice this quantity is equal to the power of p with respect to omega 1. This quantity is the power of p with respect to omega 2. And we set them equal. So that will give us, if I solve this in terms of x and y, I'll get all points p such that the powers to both circles omega 1 and omega 2 are equal. And if you expand this, you'll notice that the x squared terms cancel, the y squared terms cancel. So I'm going to get some equation ax plus by equals c for some constants. We don't really care what they are. What's important is that this is a line, which is quite surprising actually. But all the quadratic terms cancel off, so it's just linear. So that proves it. And another key condition is that this radical axis is perpendicular to O1, O2. These are the two centers of the circle. And then we can draw a few examples. So like this is the example when the two circles intersect, the radical axis goes through these 2 points because they have power 0 with respect to both circles. And then it is perpendicular here. This follows by like a symmetry argument. We know that the line must be symmetrical with respect to O1, O2, and the only one that does this is this one that goes straight down. Another case of a radical axis is if the two circles are tangent. Then the radical axis is this. I'll use a different color for the radical axis. I'll choose this color this time. This is the radical axis. This is the radical axis. Another situation, they might not even be touching. In this case, you can draw the external tangents. You know the midpoints lie on them. These are the midpoints. And you know that this is the radical axis. And then another case of two circles is when one is inside the other. However, they can't share a center. And the radical axis is somewhere here. So why is this the radical axis? Well, you can pick some point here, draw these two tangents, and they're going to be equal. So like they have the same power. So these are the 4 general cases of what a radical axis will look like between pairs of circles. So the two circles could intersect, they could be tangent, they could not intersect, they could be one's inside the other. And that's where the radical axes are going to be. And let's try to solve some problems using this. This actually appears quite frequently in geometry problems. So the first example is JMO 2012, number 1. So this problem states that I have a triangle ABC with some points P and Q, and then some points S and R. And what I know is BPS is equal to PRS. So what is the key to solve? And we also know that, sorry, this angle here is equal to this angle here. So what is the key to solving this problem? We want to show that PQRS are concyclic, so they lie on a circle. So what we can do is we can first consider this circle right here, the circle going through P, S, and R. And we don't know it passes through Q yet, so maybe we'll draw it so it misses. And what do we know about this circle? Well, we have this angle condition here. We know that this angle right here equals this angle right here. So what does that tell us? The angles, this angle equals this angle. The angles, if you look closely, this actually tells us that BP is tangent to, this is how we say the circumcircle of PSR. We put these parentheses around it. So this green circle, we know that BP is tangent to it. And I'll consider this red circle right here. This is QRS. By the angles, we also know that CQ is tangent to this circle, QRS. So now what we can say is suppose these two circles are different. PSR is not the same circle as QRS. Okay? What do we know? We know that AP is tangent. We know BP is the same line as AP. We know AP is tangent to PSR. We know that AQ is tangent to QSR. We also know that AP equals AQ. So this tells us, these three facts combined tells us, well, A lies on the radical axis of PSR and QSR. Why is that? Well, AP squared, AP is tangent to this, so this is the power of A with respect to PSR, and this is the power of A with respect to QSR. However, as some of you may have spotted now, what is the radical axis between these two circles? Well, they share 2 points. And you know if two circles intersect, then their radical axis must be the one through the 2 points. So the radical axis is actually equal to RS, the line RS. So this is telling us that A lies on the line RS. Look at our picture. RS is down here. This is line RS, and this is point A. This is clearly false. Clearly wrong. So what went wrong? Well, this assumption right here. We supposed that PSR is not equal to QSR. So this actually tells us that PSR is the same circle as QSR, which tells us that PQRS are concyclic, as desired. Okay, cool. So that's a JMO problem. A problem 1. And now we'll talk about another cool problem. This was from ARML 2019. It was from the team round. Team 10. circle. I'll try to move a bit faster. We're running a bit low on time. B, C, A, and we have a point P. Oh, sorry, this is a point T. And what do we know? We know that the perpendicular bisector of AT meets the tangent at A at some point P. And we want to find the area of PBC. And we know the lengths here. We know this is 14, we know this is 30, we know this is 40. So what's the special trick we can do here? Well, we know AT is P lies on the perpendicular bisector between A and T. So this tells us that PA is equal to PT. We also know that PA is tangent. So when you see this sort of thing, you might jump to radical axis, right? We have this tangent and we know it's equal to something. But where's the other circle? Well, the other circle is 0t. This is a circle of radius 0 at t, centered at t. Now this is a bit seemingly nonsensical, but you can just imagine like a really small circle there. And then what you'll find is that because of this thing, you'll find that the power of P with respect to omega, this circle, we know that's equal to PA squared. And we also know that's equal to PT squared. And this is like by definition, the power of P with respect to this special circle of radius 0. And this is actually a somewhat common trick, not too common, where you set a circle of radius 0 centered at a point. And this tells us that P lies on the radical axis of omega and 0t. Now this is a computational problem. I'll skip most of the details, but basically you have this circle, and then you can find the radius since you're given the 3 side lengths. You find it's like 25, and you know BC is 40, and then you know that these common tangents, you can actually erase A from the picture. And then you know that the radical axis passes through these midpoints because those have equal power, and then you know it's perpendicular to this line, so it must be this one. I'll draw it in like light blue, dark blue. And then you know that P lies somewhere here, and it actually doesn't matter because you're trying to compute the area of PBC. And PBC is only dependent on this height right here. And you know it lies on this line, so that's all you need. And then you can use similar triangles. You can compute this, you can compute half of it, compute the area. You'll get the final answer of like 800/3. That's a cool problem. And then finally, the last thing we'll talk about is the radical center. So this involves 3 circles. We've graduated again. So if you have 3 different circles, omega 1, omega 2, and omega 3, then the claim is that there are 3 radical axes. This radical axis right here, this radical axis right here, and this radical axis right here. They intersect at one point, and this point is called the radical center of omega 1, omega 2, and omega 3. Omega 1, omega 2, omega 3. And how do you prove this? Well, it's actually quite simple. So we're going to call L1 the radical axis of omega 2 and omega 3. And then we're going to define L2 and L3 the same way. This is going to be omega 1 and omega 3, omega 1 and omega 2. So this is L1, this is L2, and this is L3. And we're going to let X is equal to the intersection of L1 and L2. So we're going to let this line and this line intersect at X. And now we claim that X also lies on L3. This means lies on. And this will prove that these three lines concur. They meet at one point. And the way you do this is, well, we know that x lies on L1. So this tells me that the power of x with respect to omega 2 is equal to the power of x with respect to omega 3. And we also know that x lies on L2, which tells me that the power of x with respect to omega 3 is equal to the power of x with respect to omega 1. Indeed, this means that the power of x with respect to omega 1 equals the power of x with respect to omega 2 is equal to the power of x with respect to omega 3. Now let's look at these two. This tells us that x lies on L3 because it must lie on the radical axis. So we're done. So this proves the existence of the radical center. And this is true for any three circles. They don't just have to be in this configuration. You could have the circles like one is here, one is like here, one is here. This radical axis, this radical axis, this radical axis. They're going to meet at the radical center. You could have two of them be intersecting. They're going to meet. In any case, this is the radical center. And this one is pretty common. We're going to do one example problem, and then we'll move on to some time to do the exercises at the end. This contest is called AIME. I don't know why. But you have a triangle. You have the incircle. And then you define this point. You know that this is D. This is like the foot. And then you define this point G on the incircle such that AGD is equal to 90 degrees. That point's going to be somewhere here. And then you know the incircle also intersects at like E and F. And then the claim is that like EF intersect to DG at some point P. And the claim is that A to P is parallel to BC. On this, there's a better diagram on the handout, which I drew using asymptote. But the way you show this is you add this extra circle in. So you know this is the incenter. So you start by, okay, this is a terrible color. You start by adding in this circle. This is the incenter. You know this circle has diameter AI, since these are right angles. And then you also know that this will intersect at some point K here. And this is a right angle. And then the other circle you draw in, this is this circle right here, passing through these 4 points. And the motivation for this is in order to draw G accurately, you would want to draw the circle with diameter AD, because then this would become a right angle. And then by fact 1.2, you know this is also a right angle. And then the result actually just pops out. So you apply radical center on 3 circles. This will tell you that AK, EF, DG concur. And then since AK is parallel to BC, AP is parallel to BC. So this is one example of using the radical center. You see there's like basically one circle here, one circle here, one circle here. And then you know this line, this line, this line, they all to meet at a point. All right. And that's the end of the lecture portion for today. It lasted 15 minutes, which is quite long actually. You can go ahead and try some of the exercises. The first few shouldn't be too challenging. After that, I put some like relatively easy proof problems involving radical axis, radical center, power of a point. IMO 2012 number 5, that one's quite challenging. And then after that, there's some higher theory problems. If you want to explore more related to this, you can try to prove the coaxiality lemma, which is a generalization of the radical axis, linearity, Lahire, Newton line. You can go try those problems if you want. They do get like relatively hard. All right, that's the end of the lecture for today. Go ahead, try the problems. And they should not be very hard at the start. And feel free to ask any questions in the chat to either of us now, and we'll get back to you. All right, thanks for coming. Okay, so someone asked a question about the last part. Why AK, EF, and DG concur? Well, if you look at the three circles we drew, there's this red circle, there's this blue circle, and there's this black circle, like the in circle. And then if you look at the three radical axes, like pairwise radical axes. So if you look at the blue circle and the black circle, well, they intersect at the points E and F. So the radical axis is line EF. If you look at the black circle and the red circle, they intersect at D and G. So the radical axis is the line DG. If you look at the blue circle and the red circle, they intersect at A and K. So their radical axis is the line AK. So you know that EF, DG, and AK concur, which tells you this dotted line is actually like a full line. And since AK is parallel to BC because of these like right angles, you know that AP is also parallel to BC since P lies on it. So that's why.